There's a star dying above your head right now, not in a billion years, not in some abstract cosmic future that belongs to textbooks and telescope jargon. A star that has burned for 10 million years is currently in the final chapter of its life, and the people who spend every waking hour watching the sky are not sleeping well because of it. NASA has spoken, scientists have warned, and the question that nobody in mainstream media is asking loudly enough is this: what happens to Earth the moment that Betelgeuse finally decides it is done? Look up tonight. Find Orion. You know the constellation, the Hunter, the three belt stars, the shape that has guided sailors and shepherds and civilizations for thousands of years. Now find the star sitting at his right shoulder, that reddish-orange point of fire, that ancient, bloated, trembling giant. That is Betelgeuse. And according to the latest data coming out of NASA, the James Webb Space Telescope, and observatories coordinating in real time across the entire planet, that star is not behaving normally. It has not been behaving normally for years. And the conversation that scientists are having behind closed doors is one the public is only now beginning to hear. NASA Administrator Bill Nelson, during a recent press conference at NASA headquarters, addressed growing public concern directly. He did not dismiss it. He did not wave it away with comfortable reassurances. Instead, he acknowledged something that stopped rooms full of reporters cold. We're not predicting the explosion for tomorrow, but all signs point toward an advanced point in Betelgeuse's life cycle. Read that again. The head of NASA is not telling you that everything is fine. He is telling you that the countdown, however long, has begun. But here is where it gets interesting, because what the mainstream headline gives you is the warning. What it does not give you is the full story. The real story, the one buried inside technical papers and observatory logs and peer-reviewed journals, is simultaneously more alarming and more complex than any news ticker will tell you. To understand what is actually happening, you need to understand what Betelgeuse is, not what it looks like, what it actually is. Because once you do, the weight of this moment becomes something entirely different. Betelgeuse is a giant elderly star within the constellation Orion, approximately 642 light years from Earth. Due to being so large, approximately 700 times the size of the Sun, it is at the end of its stellar existence. Think about that scale for a moment. If you placed Betelgeuse where our Sun sits right now, its outer edge would extend past the orbit of Jupiter. The entire inner solar system, Mercury, Venus, Earth, Mars, would be swallowed whole. This is not a star. This is a furnace the size of a small solar system, and it is dying. Betelgeuse burns at about 100,000 times the Sun's luminosity. It has exhausted its hydrogen, moved through helium, and now fuses heavier elements in a core reaching 100 million degrees. Every stage of nuclear fuel a star burns through is a step closer to the final collapse. Hydrogen, gone. Helium, gone. Now it is burning through carbon, oxygen, neon, silicon. Each new fuel burns faster and hotter than the last. Each stage leaves less time on the clock. And when the iron accumulates in the core, when there is nothing left to burn, the collapse happens in less than a second. In under 1 second, a star 700 times the size of our Sun implodes. And then, in the catastrophic rebound, it tears itself apart in the most violent explosion the universe produces. When a star like Betelgeuse ultimately collapses, it concludes in a blazing supernova, an explosion so luminous that it might outshine the entire full moon for a brief time and even be seen in the daytime. Think about what that means for a moment. You would step outside at noon, squinting in the sunlight, and there in the sky, a second point of blazing light. Not a planet, not a satellite. A dead star, 640 light years away, so violently destroyed that its death glow crosses the void of space and burns bright enough to cast shadows on Earth. That is what is potentially coming. That is what scientists are monitoring, sleeplessly, with every instrument humanity has ever built. And this is where everything changes, because in the years leading up to 2025, scientists thought they understood Betelgeuse's behavior. They thought the dimming, the pulsing, the strange surface convulsions were straightforward signs of a dying star slowly approaching its final moment. They were watching a countdown, or so they believed. What they discovered in July of 2025 shattered that assumption in the most dramatic way possible. In July 2025, astronomers using the Alopec instrument on the Gemini North Telescope spotted something long predicted but never confirmed: a companion star orbiting Betelgeuse. The companion, named Sawarha, Arabic for her bracelet, is a hot blue-white main sequence star with 4-to-1. 6 solar masses. It orbits Betelgeuse every 2,100 days, roughly 6 years. For decades, scientists had theorized that Betelgeuse might not be alone. There were hints in the data, anomalies that could not be explained by a single star acting alone, but without direct visual confirmation, it remained a hypothesis. Then, the Gemini North Telescope cut through the blinding glare of one of the sky's brightest stars and found it, a small, hot companion. circling Betelgeuse in a tight gravitational dance, leaving a trail of churned gas in its wake like a ship cutting through open water. Siwarha is a low-mass star that circles Betelgeuse about once every 2,100 days. It moves through the red supergiant's vast, extended outer atmosphere, and as it goes, it stirs up the gas behind it. That weight can absorb and scatter some of Betelgeuse's light, creating the long-term brightness variations that puzzled astronomers for years. This discovery rewrote years of interpretation overnight. Every dramatic dimming event that sent headlines screaming about imminent stellar death, every pulse, every surface ejection, every brightness drop that launched 1,000 Betelgeuse is about to explode articles, now had to be re-examined through the lens of a binary system. A hidden partner had been secretly pulling the strings all along, but do not mistake this for relief. Because what the discovery of Siwarha resolves on one hand, it complicates on the other, and the complications are extraordinary. The famous Great Dimming of 2019 and 2020 was one of the most alarming astronomical events in recent memory. Back in 2019, NASA noted that Betelgeuse's brightness dimmed by about 60%, leading some scientists to wonder if it was entering a pre-supernova phase. Amateur astronomers panicked. Science publications ran urgent speculative pieces. The public briefly looked up. What was eventually determined is that a massive surface mass ejection, a phenomenon never before seen in a star at this scale, had blasted a cloud of material outward that cooled and condensed, partially obscuring the star from Earth's perspective. Betelgeuse lost a substantial part of its visible surface and produced a gigantic surface mass ejection, something never before seen in a normal star's behavior. Our Sun routinely blows off parts of its tenuous outer atmosphere in an event known as a coronal mass ejection, but what Betelgeuse did was categorically different in scale. Think about what that means. Our Sun, the most powerful object in our solar system, the engine that drives all life on Earth, occasionally sneezes. It throws off puffs of charged plasma, disrupts radio signals, lights up auroras. That is a coronal mass ejection. What Betelgeuse did was the equivalent of tearing off a piece of its own surface and hurling it into space. Not plasma, not atmosphere, surface. The star's outer layers themselves were launched into the void. No instrument had ever recorded anything like it from a star that was not in the immediate process of exploding, and scientists are still debating what it means. Because here is what the mainstream coverage missed. The Great Dimming was not caused by the companion star. The surface mass ejection of 2019 happened for reasons that are still not fully understood. The discovery of Siwarha explains the long-cycle brightness variations, the rhythmic 2,170-day dimming pattern. But it does not explain the sudden, unprecedented violence of 2019. That remains on the table. That remains a data point that has no clean, comfortable answer, and informed sources watching Betelgeuse's behavior note that those surface instabilities have not disappeared. They have continued. Betelgeuse is a variable star, so a change in its brightness is not unusual. But is it possible there will be another great dimming such as the one in 2019 to 2020? The answer, from every observatory currently monitoring the star, is an unambiguous yes. Another massive surface ejection is considered not just possible, but probable. The question is what triggers it, how large it will be, and whether, this time, it might be the precursor to something far more significant. What most people are not seeing is this. The discovery of Siwarha did not make Betelgeuse safer. It made it more complicated. And in astronomy, complicated means there are variables you have not yet accounted for, variables that can fundamentally change the outcome. Some researchers believe the two stars might merge even before Betelgeuse goes supernova. We think the stars might merge even before Betelgeuse goes supernova, one researcher noted. This would splash out some gas, spin up Betelgeuse, and potentially affect the properties of the eventual supernova. A merger between these two stars would not be a quiet event. It would be a stellar collision on a cosmic scale. The small, hot companion plunging into the vast, gaseous outer layers of the red supergiant, spinning it up, injecting enormous amounts of energy, and potentially altering the conditions of the eventual explosion in ways that are, right now, entirely unpredictable. This is not chaos. This is a system operating at the edge of our understanding, and the people who understand it best are the ones who are most honest about how much they do not yet know. Let us talk about what a supernova from Betelgeuse would actually do, not to distant galaxies, not in abstract terms, what it would do to Earth. Because this is where the real conversation lives, the conversation that is happening in briefing rooms and observatory reports. And that rarely makes it onto a news website in terms the public can engage with. Betelgeuse is too distant, more than 600 light-years away, for the explosion's damaging radiation to hit Earth in lethal quantities. A supernova would have to be around 50 light-years away to threaten our planet seriously. This is the fact that gets repeated most often, and it is accurate. Earth will not be destroyed. Life will not be exterminated. Anyone telling you otherwise is catastrophizing beyond what the science supports. But the absence of extinction does not mean the absence of consequence. And this is the part of the story that deserves far more attention than it receives. When Betelgeuse explodes, it will emit an incomprehensible burst of neutrinos, subatomic particles that travel at nearly the speed of light and pass through matter almost as if it does not exist. And these neutrinos will arrive at Earth hours before the light from the explosion does, passing through the planet and every living thing on it. They will be completely harmless. But they will be detectable. Michael Shera, curator of astrophysics at the American Museum of Natural History, has a proposal. Give him enough money, and he will build a neutrino detector large enough to tell you, several days in advance, when Betelgeuse will finally die. Neutrino detectors like the one at the Ice Cube Observatory in Antarctica are already watching. They are specifically calibrated for this event. When the neutrino burst arrives, when those ghostly particles begin streaming through the ice in unprecedented numbers, every telescope on Earth and in orbit will swing to face Orion within minutes. That is when the light arrives. And the light, according to every model scientists have built, will be extraordinary. Astrophysicists explain it would appear as another sun in the sky for months or even weeks. Dr. Michelle Thaler, the science communicator at NASA, highlighted, "It won't hurt us, but it will be the most gorgeous natural occurrence anyone alive today will ever witness." For weeks, potentially months, the sky will carry a second light source. Night will not be fully dark. The supernova remnant will be visible in broad daylight. Every culture on Earth will see it. Every religion, every government, every human being with functioning eyes will experience the same sky simultaneously. There has not been a supernova visible to the naked eye from Earth in over 4 centuries. The last one recorded was in 1604, before telescopes existed, observed by Johannes Kepler himself. But here is where the scale of this moment begins to stretch beyond the purely visual. The electromagnetic pulse of a supernova, the gamma rays, X-rays, and ultraviolet radiation will reach Earth in varying intensities over time. At Betelgeuse's distance, the levels are not dangerous to human biology, but they are detectable by every satellite in orbit. The increased UV radiation reaching Earth's upper atmosphere could cause mild but measurable changes in stratospheric chemistry. Some models suggest a slight but real reduction in the ozone layer. Not catastrophic, not irreversible, but real. Effects that would last for years after the initial explosion. And then there is the psychological and cultural dimension, the one that scientists rarely talk about, but which may ultimately be the most profound consequence of all. What happens to human civilization when the sky permanently changes? When every child born for the next 50 years grows up under a sky that carries the ghost of a dead star, a slowly fading nebula where Orion's shoulder used to be? What happens to navigation systems built around stellar coordinates? What happens to the billions of people worldwide for whom the stars carry religious and cultural significance? What happens to the collective human psyche when the universe reminds us, in the most visceral way possible, that nothing is permanent, not even the stars we have been pointing at since before written language existed? These are not small questions, and they have no answers yet, because the event has not happened yet. Now let us talk about what scientists know about the timing, and why this is the most frustrating and fascinating part of the entire story. Betelgeuse could explode tomorrow. It could hold on for another 100,000 years. That range is not a failure of astronomy. It is a reflection of genuine uncertainty about a system that is more complex than previously understood. Prior to 2025, some researchers were pointing to data suggesting Betelgeuse might explode within tens of years. Carbon-burning signatures in its core, surface pulsations, the sheer scale of its mass loss events, all of it painted a picture of a star in genuine crisis. Pre-2025 estimates from studies in 2023 suggested Betelgeuse might explode within tens of years, based on carbon-burning data and core pulsations. The 2025 discovery of the binary companion Siwarha changed everything. Its 2,170-day orbital cycle pushed estimates out to 100,000 years or more. This is the dramatic pivot that the discovery of Siwarha forced. What looked like urgent internal instability now has an external explanation. What looked like a star racing toward its death now looks, at least in part, like a star reacting to the gravitational and atmospheric influence of an orbiting companion. The timeline stretched, the urgency recalibrated, but crucially, the uncertainty increased. Because now there are 2 interacting bodies, one of which we only confirmed existed in July of 2025, and we do not yet fully understand how their interaction shapes the system's evolution. Astronomers will continue to study Siwarha to understand how it and its massive companion evolve over time. The next opportunity will be when Siwarha orbits out from behind Betelgeuse on November 26, 2027. Mark that date. Because the window that opens in 2027, when the companion star reemerges from behind the vast disk of Betelgeuse and becomes directly observable again, will provide the single most valuable data opportunity astronomers have had since the discovery was confirmed. New measurements of Sawara's mass, its orbital parameters, the chemical composition of the wake it leaves through Betelgeuse's atmosphere, all of this will allow scientists to build dramatically more precise models of what this system will do next. But 2027 is not here yet. And in the interval between now and then, Betelgeuse continues to do what it has always done: burn, pulse, eject, dim, brighten, and behave in ways that defy easy categorization. Astronomers worldwide are keeping close tabs on Betelgeuse with an armada of telescopes across the electromagnetic spectrum, coordinating in real time to catch any rapid developments. If and when Betelgeuse does explode as a supernova, it will provide an unprecedented close-up view of stellar death, something no human has ever seen with bare eyes from Earth. This coordination is unprecedented in the history of astronomy. Ground-based optical telescopes, radio observatories, X-ray satellites, the James Webb Space Telescope, neutrino detectors buried under Antarctic ice, all of them watching the same star, sharing data in real time, ready to capture the moment if and when it comes. What most people are not seeing is the competitive scientific dimension of this readiness. The supernova of Betelgeuse, whenever it occurs, will be the most studied astronomical event in human history. Every observation made in the seconds, minutes, hours, and years after the explosion will generate decades of research papers. Careers will be built on single data sets captured in the first few moments of the event. The race to observe, to measure, to be the first to publish. It is already underway. The telescopes are already positioned. The alert protocols are already written. The scientific community is already staged for a moment that has not yet arrived. And here is something that rarely gets discussed. The supernova could have already happened and we would not know it. Since Betelgeuse is 640 light years from Earth, it would take light 640 years to reach us. Let that sit for a moment. When you look at Betelgeuse tonight, you are not seeing the star as it is. You are seeing the star as it was 640 years ago. The light entering your eyes right now left Betelgeuse sometime in the 1380s, when Chaucer was writing, when the Ottoman Empire was in its early expansion, when the Black Death had only recently swept through Europe. The star you are looking at may not exist anymore. The explosion may have already happened. The shockwave may already be racing through the interstellar medium, and you would not know. You cannot know. Because the information, traveling at the speed of light, the fastest speed anything in the universe can move, has not arrived yet. This is the part of the story that tends to make people fall silent, because it forces a reckoning with a kind of distance that the human mind was not built to comprehend. 640 light years means 640 years of travel time for light itself. The fastest spacecraft humanity has ever launched would take millions of years to cover that distance. Betelgeuse is not in our neighborhood. It is not in our backyard. It is an incomprehensible distance away. And yet, and this is the astonishing thing, it is close enough that when it dies, we will see it. We will feel the neutrinos pass through us. We will live under its afterglow for months. The universe is vast enough that this dead star's light will still illuminate our nights. Think about what that means. Now consider what happens in the scientific community in the immediate aftermath of the explosion. The first alert will come from the neutrino detectors. Networks like SNOOS, the Supernova Early Warning System, exist specifically for this moment, designed to triangulate the arrival of neutrino bursts from multiple detectors simultaneously and send out rapid alerts to observatories worldwide. The last time a galactic supernova produced a detectable neutrino burst was in 1987, from a star in the Large Magellanic Cloud called SN 1987A, located 168,000 light years away. That event detected only a handful of neutrinos across multiple detectors. Betelgeuse, at 640 light years, is roughly 260 times closer. The neutrino burst from Betelgeuse's death would be extraordinary in its intensity, detectable not just by purpose-built scientific instruments, but potentially by every large underground detector on the planet. The light arrives hours after the neutrinos, and the light, in its first moments, will be a pulse of gamma radiation and X-rays that will trigger orbital satellite sensors worldwide. Ground-based telescopes will swing toward Orion within minutes of the first alert. By the time the visible light reaches peak brightness, which models suggest could happen within a few days of the initial explosion, every functional telescope on Earth will have already collected terabytes of data. The spectral analysis alone, the breakdown of what frequencies of light are being emitted and in what proportions, will tell astronomers more about the physics of stellar death than a century of theoretical modeling. And then the long vigil begins. Because a supernova is not a single event, it is a process. The initial explosion is followed by a glowing remnant that fades over weeks and months, eventually leaving behind either a neutron star, one of the densest objects in the universe, a city-sized sphere packed with more mass than the sun, or a black hole. Which one Betelgeuse leaves behind depends on its exact mass at the moment of collapse, a number that astronomers are still not entirely certain of. Current models place Betelgeuse in a stable helium burning phase, with hundreds of thousands of years likely remaining, but models are built on the data available at the time they are constructed. Every new discovery, like Sawarha, forces those models to be rebuilt. This is the nature of the science. It is not a failure. It is the process by which human understanding expands, imperfectly, iteratively, constantly revised in the light of new evidence. But it does mean that anyone who tells you they know exactly when Betelgeuse will explode is telling you something that no one on Earth actually knows. The honest answer, the one that informed sources give when pressed, is that we know this star is dying. We know it is in its final evolutionary phase. We know that final in stellar terms could mean tomorrow or could mean 100,000 years. And we know that the discovery of Sawarha has introduced new variables that make even that wide range less certain than it appeared 12 months ago. Despite the warnings, NASA stresses that there is no reason for panic. The explosion could happen next week, next year, or 100,000 years from now. But the accumulating signs suggest that the countdown, however long, has begun. That sentence from NASA's own public communications deserves more weight than it typically receives. This is not a dismissal. This is a calibrated statement from the agency responsible for humanity's understanding of space, acknowledging that the signs are real, the data is accumulating, and the direction of travel is unmistakable. The question is not whether. The question is when. And the answer to when is one that may not come with any warning at all, or may come with hours of neutrino-based advance notice. Either way, the event itself will be instantaneous at the stellar scale. In less than a second, the most energetic thing that has happened in Earth's observable sky in 4 centuries will begin, and the light from it will reach us 640 years after the moment it started. What does that do to us as a species? What does it mean when the sky, that constant backdrop that every human civilization has looked up at and found meaning in, suddenly changes in a way it has not changed within recorded memory? Every constellation has looked the same to every human being who has ever lived, give or take the slow drift of stars across geological time. Orion has looked like Orion to the ancient Egyptians, to the Greek astronomers, to medieval navigators, to your grandparents, to you. When Betelgeuse explodes, Orion as a shape will eventually be altered. The bright red shoulder of the hunter will first blaze impossibly bright, and then, over years and decades, fade to a faint smudge of nebular gas. A constellation that humans have named, navigated by, told stories about, and worshipped under, for tens of thousands of years will be permanently changed. Not destroyed, but changed. And every generation that follows will grow up with a different sky than every generation that came before. That is not a crisis, but it is not nothing either. The scientific community is preparing for this moment with everything it has. Astronomers are already planning new observations to coincide with Sawarha's reemergence in 2027, which will give them another chance to observe how it shapes Betelgeuse's atmosphere. The data collected in 2027, when the companion star swings back into direct view, will be the most important astronomical data set of the decade. It will either confirm or overturn current models of how this binary system is evolving. It will either narrow or widen the uncertainty in the explosion timeline. It will either reveal new surface instabilities on Betelgeuse or show a star that is, for now, stable and continuing its slow burn through the remaining nuclear fuel in its core. But there is a question that none of the data from 2027 will answer. And it is perhaps the most important question of all. It is not a question about stellar physics or orbital mechanics or neutrino flux. It is a question about what we choose to do with the knowledge that a star is dying, that the universe is indifferent to the timescales that feel enormous to human beings but are barely a breath in the life of a galaxy, that the night sky, that ancient constant companion of every civilization that has ever existed, is not permanent, that the things we point at and name and navigate by are themselves mortal. Betelgeuse is burning its last fuel. Its companion circles it in a gravitational embrace that will end when the larger star dies. The instruments are watching. The neutrino detectors are waiting. The telescopes are ready. And somewhere, right now, 640 light-years away, a red supergiant is pulsing and heaving and shedding its outer layers into the interstellar medium. Not knowing, because stars do not know, that an entire civilization of small creatures on a small planet around a small star is watching it, waiting, trying to understand. The question is not whether Betelgeuse will explode. Every model, every measurement, every piece of data gathered from every instrument humanity has ever trained on that star agrees it will. The question is whether the light from that explosion is already racing toward us through the dark, whether on some clear night, You will step outside and see the sky suddenly and irreversibly change, and understand in an instant that you are witnessing the death of something that was burning before your species existed. That night may not come in your lifetime, it may not come in 100 lifetimes, but it is coming. And the people who are paid to watch the sky are not looking away. Neither should you.